Yes. Okay, so I'm going to start out with something you already know. These are just, slightly different than the integrals you saw before, but you already know what to do here. Again, when we evaluate a definite integral like that that has an upper and lower limit, we've gotten a number, haven't we? Right? We get a number when we're done with the process. Okay, so just a quick example. You integrate, you plug in the upper limit, subtract what you get, and you plug in the lower limit, and you get the answer. Okay, now, if we go back to evaluating an indefinite integral without any limits on it, if you remember, all we do is find the antiderivative and then add the constant at the end, right? And if you think about that, that gives us another function, doesn't it? And with the plus c, which can be any real number, you actually get a what? Family of functions that only differ by a constant. Yes? Okay, so it's just something I want you to start thinking about. That when you evaluate an indefinite integral like that, you get the antiderivative function plus c. And again, because the c can be any number, you get a whole bunch of functions that we call a family of functions, right? Okay. All right. No big deal there. I'll come back to that. Just not right now. Okay, so going back to definite integrals then. I'll take that. Just another quick example. All you do is integrate that. Okay. And after you integrate it, you plug in the upper limit of 3 and subtract what you give, and you plug in the lower limit of 0. Gives you that minus that, which turns out, if you get a common denominator, to be that. Okay? No big deal, right? All right, something like this, we're going to have to do some algebra 1 first, right? Because there's no other way to integrate that. And so what can I split that up into, Joey? What can I split that up into?
3x over root x minus 2 over root x.
So wait, 3x over
Square root of x.
minus,
2 over square root of x.
okay. And, all right, so that's what you have, right? And then, again, I haven't integrated yet. Using some more algebra 1, can I turn that into 3x to the half, guys, right? And then I can turn that into what? 2x to the negative a half, right? All right, so all that is just algebra 1, and now I just have to use the power rule by adding one of the exponent and dividing by your new exponent there. Same thing here. Add one of the exponent, divide by your new exponent. Okay. And again, I'm going to do a lot of this in my head just because I want to save time and space here. Yep. And so if you invert the 2/3 and multiply by the 3, it just turns into a 2, right? And this turns into square root of x cubed, which can be simplified into x squared of x, right? Check me on that. I kind of did a lot there in one step. And then here, if you do the similar thing, you end up with 4 squared of x, right? Okay. Right? Got it? Okay. And once you get down to there, after you integrate, aren't you supposed to put in the upper limit of 9 and subtract what you get when you put in the lower limit of 1, right? So doing that, and by the way, this becomes what? Yeah, well, yeah, 18 times 3 is 54 minus 12, right? And then 2 minus 4, which is 42 minus negative 2, which is 44. Is that right? Okay, so A lot of algebra there. The calculus is the easy step, right? The algebra is the tricky stuff. Okay, so just be extra careful from start to finish on something like that. Okay? And again, you guys, I mean, if something like that shows up on the homework, I need to see the steps, right? There. All right, now, obviously, this is an indefinite integral, right? So when I'm done, you have a pass? You can go get one. Okay, when you're done with this one, you're just going to have another function plus c, right? You're not going to get a number on this one. Everybody agree? Okay, so again, real simple. Just integrate on that using the power rule. On this, you'll have to think of your derivative rules backwards. Since you know that the derivative of tangent is secant squared, going backwards, the antiderivative of secant squared is just tangent plus, and then don't forget your plus c. Okay, so the first part of the lesson today is really nothing new. Okay, this entire first page is nothing new at all. All right, any questions? Any questions? Okay, next page. And again, I'm going to be doing a lot of different things today, okay? And then, again, I'll tell you right now, I'd probably say maybe 5 or 6 of the final exam questions will come from this lesson alone, okay? So please, please make sure you get all this, okay? All right, now look, if we take the antiderivative of little f, again, I mentioned this before, we typically get a new function which we often call big F, okay? So no big deal there, it's just what we do. So if you integrate little f, you get the antiderivative function big F, and then you stick in the upper limit and subtract what you get when you put in the lower limit, right? Okay? Right? All right, now, what would happen though, and this came up on your homework last night, what happens if we integrate a derivative like this? What happens, guys? They cancel each other out, don't they? Doesn't the integral cancel out the derivative? Right? And so what happens is this. If I integrate big H prime, don't I just get big H? Don't I? Because the integral and derivative cancel each other out. And so at that point, don't you just put in the upper limit of b and subtract what you get when you stick in the lower limit of a? Okay? All right, now stop and think about that. Stop and think about what this is right here. What is that right here? What is that? That is not really the rate of change. It's just the change in h, period. Not the rate of change, just the change in h on the interval a to b, isn't it? Because you're taking the ending h value, which is h of b, and you're subtracting the starting h value, which is h of a. So doesn't that give you the difference or the change in h on the interval, doesn't it? Yes? So the bottom line is then, and again, this will be on the AP test. They're going to give you something like that and say, explain the meaning of that. Well, if you know that that eventually will turn into this, right? If you start with that and it turns into that, well then, when you see that in the future, you're going to just recognize that as being what? Yeah, you're just going to recognize that as being the change in what? H from what? A to B. You understand? So again, if you think about where that came from, it's not something you need to memorize. It's just something you're going to recognize now that you've seen it. Right? Got it? Understand that? Okay, so with that in mind, I'm going to move to some applications, okay? And again, I just want to emphasize one more time what I just said, and that is integrating a derivative or rate function gives you the change in the original function from a to b. Would you agree with that statement? Yes? Okay, so, all right, then let's just go through some examples. Thank you. Suppose V is the volume of water in a tank at time t, then obviously its derivative would be the rate at which the volume or amount of water is changing. Would you agree with that? Yes? If V is volume, then V prime is the rate of change of the volume. Yes? Okay, so then what would happen if I integrated V prime from one time to another time? So from time 1 to time 2. Well, thank you. Well, again, going through what I explained up here, when you integrate V prime, don't they cancel each other out, giving you V? Yes? And then you plug in the upper limit and subtract what you get when you plug in the lower limit, and you end up with this, right? So once again, what does that represent? Well, if you realize it turns into this, then you should be able to look at that and realize if you're taking the ending volume minus the beginning volume, that's going to give you the what? The change in the what? Change in the volume, in other words, a change in the amount of water in the tank from time 1 to time 2, won't it? Everybody agree with that? Okay, and again, the reason that happens is if you look at the units, what would be the units on V prime? What would be the units on V prime, for example? Maybe gallons per minute, for example? Yes, it's a rate, so it might be gallons per minute, for example. And what happens if we integrate gallons per minute? We end up with what? Gallons, right, guys? Don't we? Yes? Because you go from the rate function back to the original function. So the original function would have been gallons if the rate was gallons per minute. Do you understand how we're going back and forth here? Yes? Okay. So again, the bottom line is this, guys. On the AP test, if they ask you what that represents, you would write down what in sentence form? You'd write down what? The change in what? The volume, or in other words, a change in the amount of water from time 1 to time 2, isn't it? All right, let's look at another one. Suppose n is the population, okay, at time t. Then n prime of t would be the rate of change in the population. Everybody agree with that? Yes? Okay. Thank you. And then at that point, if you integrated n prime, you get n, right? Yes? Because antiderivative and derivative cancel each other out. And then you end up plugging in the upper limit and subtracting what you get when you plug in the lower limit. So the bottom line is this turns into this, doesn't it? Which you should recognize as the what? The change in the population from time 1 to time 2. If you take the ending population minus the starting population, doesn't that give you the change in population? Doesn't it? Yes? Okay, and again, if you want to see why this works, if you want to get units on your answer, just think about it. Suppose the units on n prime were people per year. Well, if we integrate people per year, we end up with what? People. Okay? All right, another example. Now here's where it's going to get tricky, guys. And this is what they're going to try and do to you on the AP test to try and trick you. Watch. Suppose they tell you right in the beginning of the problem that I is the rate at which cars pass through an intersection. Notice, they don't label it as I prime. They just label it as I. Okay, so they don't label it as a derivative, but they tell you it's a rate, which means it is a derivative, even though it's not labeled as a derivative. Is that clear? Yes? You see how they're trying to trick you? Yes? And so if you integrate I, in other words, if you integrate a rate, okay, maybe, for example, I is in cars per hour. So if you integrate R, which might have units of cars per hour, for example, what do you end up with? You end up what? The number of cars, or in other words, you end up with the change in the number of cars from time 1 to time 2. And what does the change in the number of cars from time 1 to time 2 represent? The number of cars that have what? Passed through the intersection during that time interval, yes? Do you understand? Okay, so again, they'll give you something like that and they'll say, explain the meaning of that integral. And you'll say it's a number of cars that have passed through the intersection on the time interval, time 1 to time 2. And again, why? Well, because if I has units of cars per hour, when you integrate cars per hour, you end up with what? Cars. And then you're putting in the ending time and subtracting what you get when you plug in the beginning time, which gives you the change in the number of cars, yes? Or just the number of cars, right, that pass through the intersection during that time, yes? Got it? So again, this was a trick right here. Even though I was not labeled it as a derivative, it should be thought of as a derivative since the direction said it was a rate. Is that clear? Watch for that. That's been happening more and more lately. They don't label it as a derivative, even though it is. Is that clear? All right, so get another one. All right, suppose a particle is moving back and forth along a straight line. Suppose S is a position at time 2, then S prime would be the rate of change of the position, or velocity, right? And so, again, that would be the rate at which the particle is moving. So therefore, if you integrate velocity, you end up with what? Position. You already know that, right? Remember this? Position, velocity, acceleration. When you go this way, you what? Differentiate. When you go that way, you what? Integrate. So if you integrate velocity, you get what? Position. Okay, so you get position S. And then when you plug in T2 and subtract, you're going to plug in T1. Think about that. Isn't that a change in the position on the time interval? Isn't it? If you take the ending position minus the starting position, that gives you the change in the position on that time interval. And again, by the way, this has a name that I'm going to be talking about on the entire next page. So the change in the position has a name. It's called what? The what? Displacement. Okay, so that's a new term I expect you to know, because on the final exam and on the next test, I'm going to ask you for displacement. You got to know what that means. So displacement is just the what? Change in the position on the time interval. And how do you find it? By what? Integrating the what? Velocity on the time interval. Is that clear? Okay? All right, and again, why does this work out the way it does? Well, again, look at the units. Suppose V has units of centimeters per second. What happens if we integrate centimeters per second? We get what? Centimeters. Okay, what if you integrate bugs per year? What do you get? Bugs. What if you integrate cooperation points per minute? You get what? Cooperation points. Got it? Okay. So if I integrate the rate at which you're losing points from time 1 to time 2, that'll give you what? 0. Probably. But in general, what will it give you? The amount of points you lost on that time interval. Yes? Right? Okay, good. All right, so okay, is it on now? Yeah. Okay. Yeah, I can't tell because I'm hearing myself talk instead of the speaker. Okay. All right, so let's do an example. Ready, guys? Okay, so suppose V is the velocity at time 2, then V prime would be the what? Again, when you differentiate V, you get what? Acceleration. Okay. And so V prime or A is the rate at which the velocity is changing, isn't it? Isn't that what acceleration is? Or V prime? Isn't that the rate at which the velocity is changing, right? So what would happen then if you integrated the acceleration from one time to another? Well, when you integrate acceleration, you get what? Velocity. And then when you plug in the upper time and subtract the lower time, you get that, which is the change in the particle's what? Velocity from time 1 to time 2. Does that make sense? Okay? So it's really, everything I'm doing on this page is the same thing. If you just consider the, that a rate, when you integrate a rate, it goes back to the original function. Okay. All right. So again, there's that again. I just mentioned it. Okay. Okay. So now, let's look at an example. Suppose this is the velocity graph for a moving object that's moving along a straight line. Okay. What I'm going to do for a second here is I'm going to label the areas between the curve and the x-axis. Is that clear? Yes? Okay, now, so the value of this would be represent what then? If you integrate the velocity, what are you supposed to get when you integrate the velocity? You're supposed to get what? Position, right? And specifically, once you plug in the upper limit and subtract what you plug in the lower limit, that would give you the change in the position, which again is called the what? Displacement. Okay, so then in this example then, The displacement, again, can be found by integrating the velocity on the time interval, right? Which in this case would be what? Finding this area, A1, subtracting A2, and then adding A3. Would everybody agree with that? Yes? Okay. So again, just to summarize what's happening with the particle that I said is moving along a straight line, the particle moves forward A1 units, then moves backwards A2 units, then moves forward again A3 units. So the particle is now this value units away from where it started. Would everybody agree with that argument? Yes? Which is why we call it the displacement. From start to finish, it got displaced that total amount. Would you agree with that? So don't memorize here. Think about it. If you think about it, there's really nothing to memorize there. Okay, now, what's the difference between displacement and distance traveled? Because again, I'm going to have both of them on the final exam. So you better know the difference between displacement and distance traveled, and please do not get them confused. Okay, so we wanted to find the total distance traveled, not the amount it was displaced, but rather the distance it traveled. So when you talk about distance traveled, you got to consider all the backs and forths, yes? So what I'm saying is this. We need to count area 2 as being a positive number. In other words, displacement in this case would be the antiderivative of the absolute value of the velocity. So the only difference is that for displacement, you don't have absolute value on the velocity. And for distance traveled, you do need an absolute value on the velocity. So it would end up being just A1 plus A2 plus A3. Okay? Is that clear? In other words, guys, what you're going to have to do is you're going to have to take area 2 and flip it up so that you're counting it. So let me give you an example then of what I'm talking about here. Suppose a particle moved forward 3 units, backwards 5 units, and then forward, I don't know, 10 units or whatever. Okay? What's the displacement? Okay, hold on. Well, it went 3 forward, 5 back, and then 10 forward. And what does that equal? 8. So it's now 8 units forward from where it started with. How do I know it's 8 units forward? Because displacement turned out to be what? Positive. So it's 8 units forward from where it started. That's what we mean by displacement. But what would be the distance traveled? Well, in that case, you'd have to take this negative one and make it positive. That's where the absolute value comes in. Is that clear? So we'd take any negative one and make it, any negative area and make it positive by flipping it upward graphically. Wouldn't that make it positive? If you take a negative area and flip it up by taking the absolute value of it? And so now the distance traveled would be what? 3 plus 5 plus 10, which is what? 18. You see the difference between displacement and distance traveled? Yes? It went, so it moved 3, then it moved 5, then it moved 10. So it moved 18 units altogether. That's the distance traveled. Do you understand? Okay? All right, now here's another mistake you're going to make if I don't stop you right now. That right there is not the same thing as that. So you can't just integrate the velocity and take the absolute value when you're done. Clearly that won't work. For example, if you tried to do that here, you would get 8. Is that the distance traveled? Is it? Is 8 the distance traveled? No. So you can't just take the absolute value at the end. You got to integrate the absolute value of the velocity. So the absolute value has to be on the what? On the inside of the integral, not on the outside. It's not the same thing. Is that clear? Yes? Okay. All right. So let's do some specific examples now. This is what, you know, the problem's going to look like on the final exam. I'll tell you that right now. Okay? So suppose I give you this as the velocity function for a moving object that's moving along a straight line. T is in seconds, V is in meters per second. Find the displacement for the first 6 seconds. So here's time equals 0. Here's time equals 6. Everybody with me? Okay, so to find the displacement or distance traveled, clearly I need to find these areas. So what's this first area here, guys? What is that? It's just 1/2 2 times 3. So what is that? What is it? 3? And because it's a positive area, right, it's above the x-axis, the displacement is going to be what? 3, and then minus, why am I subtracting? Because this area is what? Negative. And what's that area? Well, you got 6 square units here, and you got what? 3 square units here, and so that's what? Minus 9, which equals what? Negative 6. What are the units? Meters? Yes? So it went 3 units forward, 9 units back, so it's now displaced 6 units in a negative direction from where it started. Everybody agree with that? Okay, now, how would you get distance traveled? It would be what? 3 plus 9, which is what? 12 meters. Does that make sense? Yes or no? Good? Okay. Good? Yes? Easy, right? Okay. All right, now I'm also going to put one of these on the calculator part of the final as well as the next test, and so you should be able to handle that as well. So suppose I give you the velocity function, I let you use a calculator. Well, here we go. First thing you want to do is put it in y1, and make sure you're in radian mode, by the way. Okay, so all I did is put the velocity function in y1. Now I want to find the displacement over the time interval 2 to 4 minutes. Got it? And so since I let you use a calculator, what I'm going to do is just integrate that on the home screen. Where's the integral again? Alpha window, number 4, right? Okay, so, and by the way, just make sure I'm in radian mode. I am. Okay, do me a favor, put it right in front there. Yep, thanks. Okay, so, and here I go to what? Alpha trace and choose y1. Okay, does everybody agree that will give me displacement? Yes? Okay or not? Okay, hit enter. Negative 0.8063, or sorry, just 0.80, negative 0.806, what is it, meters? So what that means is the object or particle is 0.806 meters backwards from wherever it started. Yes? And then for distance traveled, we need to put absolute value. Where's absolute value? Math over to NUM, yes, and then choose number 1. Is that where absolute value is? And then you can put in Y1, right? How you doing? Okay, thanks. Ryan, I think this is all yours. Yeah, looks like it. I think. Yeah. This is all yours. Okay. Okay, guys? And then you hit enter. So again, you got to be patient sometimes with integrals. They take a while. Don't start pressing buttons. You're going to freeze it. There it goes. So 1.783 meters is the distance traveled. Everybody good? Yeah? So 1.783. So again, you should be able to handle this very easily if you know the difference between distance traveled and displacement. Okay? All right. Are we on the last page? Are we? Okay. That's good. I don't know what it is with these lessons. They've been going faster than I ever remember. I don't know why. Okay. Not bad, right? It's not a bad thing. Okay. Okay, so now, again, this is not a calculated problem. So what would we do here? Well, obviously that's a parabola, right? Shifted what? Shifted 1 unit down and opening upward, right? So to graph it, obviously it's going to pass through the point 0, 1, but let's get some other points. When I put a 1 in for t, what do I get? 0. And by symmetry, won't you have another point over here? Okay, let's do one more. When I put a 2 in for t, what do I get? What do I get? 3. So I get 2 comma 3 and so on. Okay. Okay. And again, this is going to keep going up like that, right? Okay. Now, I want to find the displacement for the first what? 2 seconds. So basically, I would have to take this area with a negative on it and then add this area, wouldn't I? Yes? Everybody agree? And so the bottom line is this. Displacement is just the antiderivative of the velocity, yes? Yes? Agreed? Agreed? Okay. And so, you guys, since there's no absolute value on this, I can just blindly integrate this. I don't even really need to know what the graph looks like for displacement, do I? Because it'll always be just the antiderivative of the velocity, yes? Everybody agree with that? So I really don't even need to know what the graph looks like to do that. So let's just go ahead and do it. And then you plug in the 2, 8/3 minus 2, and then subtract what you get when you put in the 0. And so what does that turn out to be? 8/3 minus 6/3, which is what? That's an 8, by the way. 8/3 minus 2, which is what? 6/3? Or so 8/3 minus 6/3 then is 2/3. Okay. Feet. All right, again, do you understand, guys, that I really don't need to know what the graph looks like for displacement? I can just blindly integrate the velocity from one time to the next, and that will always correctly give me the displacement. Yes? Yes? Okay. Now, for distance traveled, that's a different story. Because in order to integrate that, you can't integrate it with the absolute value in there, can you? No. And so without a calculator, you're going to have to do some thinking here. Okay, you can't integrate it with that absolute value in there. So what I'm going to do is this. Think back to Algebra 2 and understand that graphically, what does taking the absolute value of a graph do? It takes any piece of the graph that's below the x-axis and does what to it? It flips it what? Upward. And so it'll take what would have been a negative area and making it positive, right? So if the area would have been -3, basically it makes it +3. So what's a way to get from -3 to 3 without putting an absolute value in there? Put a what? A negative on it, right? Can't you just put a negative on it? Yes.
For A, I think it should say minutes where it says seconds in the problem.
Oh, yeah.
Like in the problem.
Yes. Okay, let's say minutes. Sorry, thank you. All right. Good? Thank you, Joe. All right. All right. So again, what I'm saying is this then, guys. You can't integrate with that absolute value there. So one way to get rid of the absolute value is to look at the graph and make any adjustments you need to make. So what I'm saying is this, that first area that goes from 0 to 1, if I integrated that, okay, I'm not going to do it right now, but if I integrated it, it'll be negative, won't it? Won't it be negative? Won't that end up being negative because the region is below the x-axis? So how can I make it positive? By putting a what out front? A negative. So it'll take a negative times what would have been negative and turn it into a what? Positive area, which is what I need it to be for distance travel. Does that make sense? And then you can just add what you get when you integrate from 1 to 2. And do I need to do anything special there? No, because it's already above the x-axis. So when I integrate that, that'll turn out to be a positive number. So now you have this positive distance plus this positive distance, which will give me the total distance traveled. Does that make sense? Okay, guys? I'm not going to finish it. You could do that if you needed to. I'm not going to finish it. But again, I want you to understand that when I integrate this, it'll be negative, but then when I multiply by the negative that I stuck out front, it'll turn into a positive distance. Do you understand why I did that? Without just memorizing? Yes? Okay, let's finish this up. All right, I'll tell you right now, guys. If you go on the AP website and look at the AP Calculus AB webpage where it lists the major topics students should know, this, believe it or not, is its own topic right here. This is its own topic. It comes up so much on the AP exam in different ways that, again, they list it as its own topic that students should know. Okay, so that means it's going to come up a lot on the final exam and a lot on the next test. And when I said earlier that there's 5 or 6 questions on the final from this, that might be an underestimate. I think it might be more. I don't remember. Okay, but this is definitely going to be on there a lot. Okay, so, and again, I don't want you to memorize. If you try and memorize it, forget it. You're not going to remember it. You're not going to understand it. You're not going to know when to use it. I don't want you to do any memorizing here. I want you to think about what I'm about to explain, and then hopefully from there it'll just make sense and it'll stick. Ready? Okay. Suppose we know the value of f of a, and we want to find some later value f of b. This should make sense to you, that we can find the later value f of b as follows. Okay, so to find the later f of b value, you can take an earlier function value, like f of a, and then add the change in f from a to b. Does that logically make sense without memorizing it? Yes? Okay, now let me ask you. Didn't we talk about earlier how to find the change in f from a to b? How? By integrating what? How do you find the change in f from a to b? By integrating what? Yeah, integrating f prime from a to b. Isn't that what I started out with earlier in the hour? Okay? So the bottom line is, to get some later function value f of b, you take some earlier function value f of a, and then you add the change in f from a to b by integrating f prime from a to b. Is that clear? Yes? Okay, so again, that should make sense to you, and so you should not have to memorize it. It should just make sense. And again, I know this from here to here made sense earlier to you as I explained it. Okay, you were all nodding your heads earlier when we talked about how this gives you the change in f from a to b. So it should still make sense. Does it? Yes? Okay, so let's just do these 3 examples and we'll be done. Hang in there, guys. Here it goes. All right, so look what I give you, guys. I give you f prime. I give you f of 4, and I ask you to find f of 5. So this is how it should logically set up. To get the later value f of 5, you take the earlier value f of 4, right? And when I talk about earlier, that's just my way of saying it's to the left on the number line. Is that clear? Yes? Okay? So to get some later function value, you take some earlier function value, like in this case, you can use f of 4 since you know it. And then you would add the change in f from 4 to 5. And how do I get the change in f from 4 to 5? By integrating what? Integrating what? F prime from 4 to 5. Again, when I integrate f prime from 4 to 5, it gives me the change in f from 4 to 5. Doesn't it? Okay, so let's just do it. Okay, so f of 5 is what I'm looking for, so leave that alone. I know f of 4 is negative 7, so put that in. And then this is something I can find, isn't it? So what do I get when I put in a 5 there, guys? Quick. You can do it in your head. 25 minus 15, which is what? 10. Minus what I get when I put in a 4. What do I get when I put a 4 in there? 16 minus 12, which is what? 4. And so what do you get? What do you get? So negative 1. Any questions on that? So do you see what I did? Yes? Okay, 2 more. So we're going to use a graphing calculator. Okay, so I want to find the value of f of 1 and I gave you f of 3, and I gave you f prime. So how is this going to set up, guys? What's the later function value, f of 3 or f of 1? What's the later function value, f of 3 or f of 1? F of 3. So the later function value, f of 3, can be found by taking the earlier function value, which is f of 1, and then add the change in f from 1 to 3. And how do I get the change in f from 1 to 3? By integrating what? F prime from 1 to 3. Does everybody see why he set it up that way? Yes or no? Yes? Good or not? Good? Okay. And by the way, f of 3, I know this time. What is f of 3? 6. I'm looking for f of 1, so leave that alone. And then this is something I can find on my calculator, can I, since I'm letting you use a calculator? So, here we go. Do this, guys. Sine of x squared. Be careful. You need a parenthesis there. Make sure you add that parenthesis, okay? And so what do you get? 0.463. Okay, so any questions on that? And so how do I finish solving for f of 1 at this point? What do I do to finish solving for f of 1? Subtract that. And what does that equal, guys? What does it equal? 5.537. Understand, guys? Okay. And by the way, I think there is a displacement and distance travel problem or two on Friday's packet. Okay. So for people who aren't here, you can help them out. But it looks like everybody eventually showed up, I think. Yeah. Okay. All right. One more, guys. All right. Again, there's plenty of these on the AP exam as well. So what would you do? You have the position at time equals 2, so you have s of 2 is 10. You want to find the later position, s of 5, right? And you got v. And so the later position here, which is the later position again? What is the later position, s of 2 or s of 5? Yeah, s of 5. That's the one later on down the road on the number line, right? So to find the later position, s of 5, you can take an earlier position, like s of 2 in this case, and then you want to add the change in the position from 2 to 5. How do I get the change in the position from 2 to 5, guys? By what? Everybody, come on, this is my last question. I want to make sure you all get it. How do I find the change in position from 2 to 5? By doing what? Hello? Everybody. By what? I'm still only hearing like 5 people. I have to what? Integrate the what? The derivative, which is the what? The velocity. Right? From what? 2 to 5. So again, to get the change in the position from 2 to 5, I integrate the derivative of the position, which is the velocity. So I just integrate the velocity from 2 to 5, yes? To get the change in position from 2 to 5, right? And so this is s of 2, you know. S of 5 you're looking for. And so now I just need to punch this into my calculator, right? Yes? Whoa. I'm telling you, all kinds of weird stuff is happening today. Things are graphing themselves. Microphones are going off on their own. Remember, it went off by itself, and the graph was graphing by itself. Okay. Okay. So, real quick, guys, I'm just going to do this, and then I'll be done. Hang in there. All right? Did I do that right? Is this good, guys? And so what is that, 7.5? Yes? And so what is s of 5, guys? In other words, what's my position at time equals 5? 17.5. Okay? No, there's nothing here that's that hard. It's just that there's a lot here. Yes? So, again, you'll need to look this over again when you're doing your homework tonight and when you're doing that packet on Friday. And again, I will be collecting homework right after break. Okay? It'll be, you know, one or several of the last 3 assignments I've done in this new unit. Got it? Right? Have I done 3 units or 4? 3 since the last test? Okay. Right. Or I might wait till I teach the 4th unit and then collect it. I'm not sure. But the bottom line is you got to keep up on your homework, right? Okay, so take a break for a couple minutes and then you can get started on your assignment.